Okay, so we don't need to worry about that. That's good, because I prefer not to be on the camera. Okay, I'll start off with our introduction. Welcome to McCarthy Observatory, our second Saturday Stars event for February. My name is Parker Moreland. I'm one of the volunteers here for the last 17 years, and I'm your storyteller for tonight. So, I'm going to give you a long story. It started 100 years ago. It accelerated and got really serious about 50 years ago. And it's going to be, in addition to being very long, it's going to be very technical. Okay. And we can draw us the lights now, Steve. I have a PhD in physics from 50 years ago. In all that time, I have never had to use general relativistic gravity that Einstein predicted 100 years ago. I've been able to do everything I need to do. NASA has been able to explore the entire solar system with good old Newtonian gravity that we learned in high school many years ago. I have taught college physics, I've taught high school physics, never needed to know the general relativistic version of Einstein's gravity. But to understand what we're going to talk about tonight, we're all going to have to start thinking that way. We're going to help you with some artist conceptual drawings and what have you as best we can. But believe me, they are not perfect, and you are going to have to use your imagination and think outside the box to try to understand what was going on a year and a half ago when we first detected gravitational waves. What happened? 1.3 billion years ago, two orbiting black holes, each about 30 times the mass of our sun, finally spiraled together and merged into one big black hole, releasing huge amounts of gravitational wave energy. Energy equivalent to 3 solar masses. Just use E equal mc squared if you want to find out how much energy that was. 3 times the mass of our sun, you can Wikipedia that, was released in 0.2 of a second when that merger happened. And you're going to see the merger in several ways. So on September 14th of 2015, an extremely tiny fraction of the energy in that 1.3 billion, I left out the B, billion light year radius spherical wave, now looking more like a plane wave as it passes Earth because it's come 1.3 billion light years, passed through a special detector in Livingston, Louisiana. We're going to talk a lot about that later. And traveling at the speed of light, the same wave passed through a similar detector in Hanford, Washington State, 7 thousandths of a second later. We're going to call that 7 milliseconds. Milli is the prefix for 1/1000th in science. So we're going to be calling that 7 milliseconds from now on. And it turns out the light travel time from Livingston, Louisiana to Hanford, Washington is 10 milliseconds. So it was coming in at an angle. It wasn't coming in along the line path between Livingston and Hanford. It was coming in from the side. Didn't take quite as long. Okay, and you can think about that as we go along too. Later analysis showed that the binary black hole was about 1.3 billion light years away. We've already said that, which is about 10% of the way to the edge of the observable universe. We consider that to be about 13.7 billion light years away. The gravitational wave, hereafter to be known as the GW, came roughly from the direction of the Magellanic Clouds in the southern hemisphere. They figured that out from that 7 milliseconds that I told you. Our story for tonight, which involves a 50-year journey to the Laser Interferometer Gravitational Wave Observatory, LIGO for short, Now back to basics, and then we'll start the journey. You all know about mechanical waves, sound waves that we detect with our ears, seismic waves through the earth, ocean waves, all of these different kinds of mechanical waves we are very familiar with. We have become very familiar with electromagnetic waves. They were predicted theoretically by James Clerk Maxwell in 1873, and just a few years later, 14 years later, they were found experimentally by Heinrich Hertz. And since then, we have gone gangbusters with electromagnetic waves. Radio, TV, radar, cell phones, Wi-Fi, all of those things operate on electromagnetic waves. And of course, all the light that we see is an electromagnetic wave. The heat that it radiates from the fireplace to our bodies is coming in an infrared electromagnetic wave. It's all around us, and we'll take a look at that in a minute. But gravitational waves were predicted theoretically by Einstein in 1916, 100 years ago, and they were just found experimentally last year. It took a long, but they are so hard to find compared to what was done up here. It has taken a long time to develop instrumentation able to do it. Here's the electromagnetic spectrum that you may be familiar with or may not be. It goes from radio waves, starting about 1 cycle per second. We represent it this way, and each of those peak-to-peak distances is called a wavelength, and that's 1 cycle. Radio waves get as low as about 1 cycle per second, or 1 hertz. We use the word hertz for cycles per second. And then we go up to the microwave. Now we're up into the gigahertz, 10 to the 9th, one with 9 zeros after it. And that's where your cell towers and all that sort of thing is working. Your microwave ovens, all of that. And then we get into infrared. I told you that's basically heat radiation. A lot of stuff from the sun comes in infrared. The visible band is really a really small section, but important, of course, to us. We developed in such a way that we can sense the visible light, visible electromagnetic waves. We can't sense any of the others with our body. Then ultraviolet, the sunburn effect, also coming from the sun. Then X-rays and gamma rays. Now, if that's 1 hertz over there by the lowest frequency radio waves, this is one with 20 zeros after it, frequency, cycles per second, hertz, over here. It's a huge range in frequency. Okay. This is 1 order of magnitude here, from here to that over there. But in reality, when you go from radio to gamma rays, you have 20 times that much. Now here's good old Newton's gravity, which we've been living with, and I mentioned earlier. I have lived with it all my professional life. He just said that all massive objects attract. And that means the sun attracts the earth attracts the moon, we attract each other. And he said that the force of attraction is proportional to the product of the 2 masses involved, sun mass and earth mass, for instance, divided by the separation between them squared. Okay, and when you plot that for any 2 masses against the separation, this is what it looks like. Of course, as you get to very, very small separations in the denominator, you get a very big force, correct? But then, because of that square law, it drops very, very quickly and goes down and then goes more slowly, and you'll notice it never quite goes to 0. Never. Until you get infinitely far apart, far away. And that's a theoretical concept. And that's why even Neptune feels the gravitational force of the sun. It's very far away, much further than we are, much further than Mercury, but there is still gravity way out there because it never really goes away. And this is Newtonian gravity, which we found out about 300 years ago. We have explored the entire solar system. NASA has explored using this concept of gravity. Now, there is a little bit, there's part of general relativity that deals with space-time, and it turns out the guys who run the GPS system, which NASA relies on, A lot of us, right, rely on the GPS system. It turns out for it to be as accurate as it is, just a few feet, spot you on Earth, they do have to make a correction to the atomic clocks which each one of those satellites carries, which is a general relativistic correction. And a fellow graduate student of mine back in graduate school 55 years ago happens to be the guy who did the math that came up with the equations that give them the corrections that they make for the GPS satellites. But it's not gravitational waves. It's other general relativistic effects with space-time. Newton also said that anytime you have a force, you have an acceleration, and it's governed this way. It's a force divided by the mass of the object that's being pushed upon, and it generates that acceleration. Now here's Einstein's gravity. Here's an attempt to show you that. He said, no. Forget about that inverse square law of Newton. Yeah, it works, but here's the right way to think about it. Consider that we're warping space-time. And here is an artist's example of that. Here's the Earth, there's the Moon, and this is supposed to be space. If they weren't there, this would be a flat cloth, mesh, whatever it is. But because of the mass being there, it has warped it like that, and you'll notice the Moon is warping a little bit over where it is. But nevertheless, that creates a force, that slope in space-time, generates a force between the Moon. And since the Moon happens to be going around us, it doesn't fall into the Earth. It just keeps going in a circle instead of going off in a straight line, which inertia would tell it to do. It was going that fast. So this is Einstein's vision of gravity. Now his math said that any accelerating mass will radiate gravitational waves similar to the way accelerating electric charges, that is to say electrons, radiate electromagnetic waves. Does anyone in here know how we generate radio waves? Let me tell you how. It does apply here. You have an antenna, let's say on the cell tower. We have a wire. The wire is a metallic conducting wire which lots of electrons in it. All of those atoms of iron or whatever have electrons. And we put a voltage on the wire that makes the electrons oscillate back and forth like this. We push them this way for a brief portion of a second, slow them down to a stop, push them that way, do the same, slow them down, and we have them oscillating back and forth like this in the wire. To do that, to be making that motion, they have to be accelerating first that way and then decelerating, accelerating and decelerating, they're both accelerations, and back and forth. So we're constantly accelerating electrons. Voila! Accelerating charge, they give off radio waves and we hear the cell tower, true? Those electromagnetic waves hit a wire in the antenna in your cell phone, cause those electrons to do the same thing at the same frequency the others were, true? You with me? And we convert that to a little voltage, and oh, you can talk to someone on your cell phone. And that's what's going on in between. The accelerating electrons are generating those electromagnetic waves that travel from the cell tower to your phone, or from your Wi-Fi router to your cell phone or your tablet or whatever you've got. We are using them all over the place, and we are awash in TV signals, satellite signals going through us all the time from space. Okay? Well, Mr. Einstein said accelerating masses do the same thing. And we just talked about that Jupiter is feeling an acceleration which holds it in its orbit around the sun. That means it's accelerating. That means it's radiating GW, gravitational waves. True? It's an accelerating mass. Earth is an accelerating mass because we're also going in an orbit around the sun. Were you with me? They're all accelerating masses. And Einstein said, anytime you have one accelerating, you're going to get gravitational waves. But he solved his equations and he discovered, oh, they're so small, nobody's ever going to see them. No one is ever going to see them. The effect is so small. And we will never see the waves from Jupiter, by the way. Wait till I tell you what we did discover last year. So enter the Laser Interferometer Gravitational Wave Observatory, started being built in 1994. It's called LIGO. You'll hear that word an awful lot the rest of the evening. That's what made the discovery. The LIGO team had to do two things to find these very, very weak gravitational waves that Einstein thought that would never be found because they are so small. They built the most sensitive scientific measuring instrument ever invented. You're going to learn a lot about that. And they looked for some of the largest accelerations of mass in the universe, the merger of two orbiting black holes, or the merger of binary neutron stars, etc. It turns out this is the one they found, two merging black holes. Okay, but they were ready to see either one of them. Now this is the gravitational spectrum I'm showing. This is sort of, remember I showed you the electromagnetic spectrum before. This is a little different. This is frequency down here in hertz. And notice there's 1 hertz there. It goes up into the audible range. You can hear up to about 20,000 hertz when you're young. Most of us probably can't hear up to 10,000 hertz. But in any event, you're in that range, and then we're down into the very, very low. This is where we're taking a year for one cycle to go, well, okay. And what we're showing here is the strength of gravitational waves. This is this range in here of frequencies would be for billion solar mass black holes. Now we know that there are black holes of that size. I don't know that we've ever seen one merge. Boy, that would be a gem dandy. But an instrument hasn't been built yet to do that. They have one on the drawing boards that would try to, but look, these limits are of sensitivity. Let me get something up here to show you. The one we're going to talk about is LIGO. See this one here called Advanced LIGO? These lines are the maximum sensitivity curves for those. And we'll notice that this yellow batch here is for neutron stars and stellar mass black holes in spiral and collision. And that's what they found. And notice that that reaches up just above the threshold for the advanced LIGO. And so our attention is going to be placed on this one. These are proposed. This is a proposed spaced interferometer that might look for things down here. By the way, look at this one. Relic of the Big Bang. But nobody proposed is sensitive enough to see that yet. So maybe someday we'll be able to see that, but no time soon. Now, here are some other things that they can see with this kind of instrumentation. But we're just going to focus in on Advanced LIGO, which is the one that found the 2 in-spiraling black holes last year. But this is what's out there for us to hope to see someday. We'll get to that later in the talk. Here's a simulation of 2 black holes spiraling around. They seem to be gobbling up a few stars in between. I want you to particularly notice, just as they coalesce into one black hole, what happens around them to the stars. There's a ring down effect, they call it. The resulting black hole kind of oscillates there, jiggles a little bit like a bowl of jello until it settles down right there. See how what's happening out here? And that's the ring down gravitational wave leaving. Okay, now we're going to get kind of technical. We're going to talk about the actual instruments that measured this. There are two Michelson interferometers. One of them is in Livingston, Louisiana. One of them is Hanford, Washington. And taken together, they are the LIGO. You need them both to really be sure what you got. The Michelson interferometer was invented over 100 years ago to show that light does not need a medium to flow in, like sound has to have air or metal or something to flow in. But it can flow, it can traverse vacuum. Light can traverse vacuum. And all the electromagnetic waves can go through vacuum. Back then they thought, oh no, it's more like sound and that sort of water waves. It has to have a medium to carry the wave. No, they prove it does not. And they use this instrument to do it. What we have is two mirrors, two identical mirrors here, regular mirrors. We have right here what's called a beam splitter. What it really is a mirror which is half silvered. That means they don't put a full coating of aluminum or whatever the silvering material is on it. And so the laser, nowadays of course we always use lasers. Back in Michelson's day they used white light. They didn't have lasers then. But now we shoot a laser beam at this, and as I have just told you, half of it is reflected up to that mirror and then bounces back. When it gets back here, half of it goes back to the laser, the other half goes down to the photodetector. You with me? Think about the other path. It goes from here to here, okay? Half of it goes through, hits this mirror, bounces back, hits this one, and now, once again, half of it goes to the photodetector, half of it goes back, is transmitted. Okay, so I've got two bunches of light, one that got through here, and one that got through here. Half the light that left here can go this way. But there is a very clever trick. When this light reflects off the mirror, its phase is reversed. Well, that probably won't mean anything much to you, but for light to reinforce each other, they have to be in phase, and if they're out of phase with each other, they cancel, and that's why the dotted line down here. If these two distances are exactly to a wavelength of light the same, nothing will come through here. But if you jiggle either one of these mirrors at all and change the path length, you're changing the phase of the light that gets to here, and now a light can start hitting this photodetector and giving you a signal. Are you with me so far? It's a very clever device. So the way they set them up, of course, initially, is everything is balanced exactly for no light. And that way, if we see a gravitational wave go by, we'll get light, and we'll know it. Okay, let's go to the next one. This is what's really built at Livingston, Louisiana, and Hanford, Washington. It looks very much like the other picture, except they've added these special mirrors here and here. Okay, and they are very, very special, and they give the extra resolution they need to see it. It is so complicated we are not even going to talk about it. They are partially silvered mirrors. They're not fully silvered like these are. And what they show here is a gravitational wave traveling in this direction right down on the thing and causing contraction in this line and expansion in this line. And that's the way gravitational waves work, but we're going to see more about that later. So this is just a picture of the actual LIGO interferometer, but it's basically a Michelson interferometer. Now I'm going to let you hear, it's a little bit commercial, but you're going to see the two guys who actually had this idea of how to measure this 50 years ago. And they're going to tell the story themselves along with some of the young upstarts that have been working on it the last 25 years. You'll see a quick overview of it from the scientists who actually did it. I think it's worthwhile.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory.
LIGO is really
This is
two
Hanford,
observatories that work in
Livingston, Louisiana.
The LIGO interferometer has arms that are about 2.5 miles long, 4 kilometers. We have a laser. The laser produces the purest light you can possibly make. Produces light that's so coherent that it's capable of detecting gravitational waves.
We have these very massive mirrors. They weigh 40 kilograms, which is 88 pounds. They're about this thick, and they're just the purest material you can imagine.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This was going to be a very high-risk experiment. It was from its very inception.
If you think about this in the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does, it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that
See the
if
light
you made
turning
this
on and
long
off?
enough, if you didn't make it a little pipsqueak thing like this, but if you made it sort of kilometer scale, you could probably get these extremely precise measurements.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
The precision that was required, it was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.
Okay, let's look a little more carefully at how the interferometer works. Oops, I didn't do it right. I gotta go back. I gotta tap here. And now we should have another. There's the light waves from the lasers. Now, See them moving back and forth, and you see the signal, that's the gravitational wave signal, as the length of those two arms changes as the gravitational wave goes through. Now we'll do it in slow-mo. Light going to that mirror, reflecting from that mirror, coming back to the beam splitter, meeting the other one, both of them, and notice how they're canceling very nicely like they're supposed to. But what happens if a gravitational wave goes through and starts changing the space between these mirrors? Notice how light starts hitting the photodetector back and forth every time they move back and forth, like that. And this is the signal they were looking for, a non-zero signal. They had some noise signals they had to fight, but they were looking for a real one, and you'll see that in just a second. So there is the aerial picture of the one in Livingston, Louisiana. You're not seeing the entire 2.5 mile length of the two arms, but that's the center building where the beam splitter, the laser, and the photodetector, and a bunch of computers is located. Here's the one in Hanford, Washington. Here you're seeing everything. You're seeing the full 2.5 miles of each of the two arms. Don't forget, you saw parts of the over 1 meter stainless steel pipes that run the full length and have an ultra-high vacuum in them, so there's nothing to impede the path of the laser beam except those mirrors. And they're inside, of course, a concrete pipe or tunnel. Okay, you're going to put on your imagination now. This is one artist's way of looking how a gravity wave would look traveling through space. It looks to me like a worm. But notice how, any one spot here, it gets long in this direction while it gets narrow here. That's a property of it, like Professor Weiss said. It's stretching one way while it's compressing the other, and they're doing this back and forth constantly. Okay. Now you'll notice this wave seems to be traveling very slow. The gravitational wave travels at the speed of light, so you're going to really have to use your imagination. This thing is whipping through space at the speed of light. So we're gonna pretend we're at the front edge of that, just in one position, and see how it would look that way. Now we're right there. Let's say that this is one of the laser beams going this way, the other one may be going that way. And you'll notice while one of them is stretching, the other one is compressing, and vice versa. Now this is the space between them. This is the Einstein idea. It's the space between them is growing a little bit, then compressing a little bit. But that's enough to change the path length for the laser light, and therefore cause signals to show up in that photodetector. Okay, another simulation of a black hole merger, and I want you to pay, the gravity waves are going to be in green. I want you to pay attention to the speed of rotation of the two black holes as they merge. It's going to get faster and faster. The waves are coming out faster and faster. They're going to be getting stronger. The color of green will get darker as it gets stronger. And then I want you to look at the ring down. It's just, we saw it earlier, but just as the two black holes merge, I want you to look at what happens to the so-called ring down gravitational waves. Oops, didn't do it right, sorry. Okay, now you see one is a little bigger than the other. They decide that one of the two that merged was 36 solar masses, the other one was 29. So this is trying to depict that. As they get closer and closer, they speed up. The gravitational waves get stronger and closer together as they leave. Things are beginning to happen. Look, look. Now, there's the ring down. See these gravitational waves here? And then once the bowl full of jelly gets solidified, no more gravity waves are leaving. It's just sitting there. It's all over. Don't forget, that interesting part happened in 0.2 of a second. So here's the data. The red data here is the output of that photodetector, just a voltage, okay? And that entire span is a little over 0.2 of a second, okay, on there. And so what's happening, this is noise in the background. They really work to get rid of the noise, but there's still a little bit left. And then all of a sudden the gravity wave starts coming in, starts building up, starts getting a little faster. You notice how the peaks are getting a little bit closer together, closer, closer, and you saw that happening in the simulation too. And then we get to about here and it's all over. It has merged, and here's the ring down right here, and then noise again. You with me? This is the signal that all of this has come from, September 14th, 2015. Now the same thing was going on in Livingston, Louisiana. The blue curve is the Livingston, Louisiana photodetector output. And you'll notice it looks very, very similar to the one in Hanford. In fact, they have overlaid in orange the one in Hanford. Okay, you see the orange behind the blue? And you notice how they are very, very similar. They're going up and down in synchronism. Now, down at the bottom in the note here, it says shifted and inverted. They had to invert it simply because of an instrumental thing. But the shift is, remember I think I told you, it took 7 milliseconds for the wave to go from Livingston, Louisiana to Hanford. So it would have gotten there a little later. They have moved it over the 7 milliseconds to give us the nice overlap picture that we're seeing here, just to show you how good the overlap is. Now, in the last 20 years, the astrophysicists and the special relativity theorists have gotten very good at modeling things in the cosmos. The merger of black holes, the merger of neutron stars, supernova explosions, this sort of thing, relativistically, and model what would happen. These nice smooth curves down here are computer simulations using all of that theory that I think I may have told you, 1,000 people around the world were involved in this experiment. Physicists, astronomers, mathematicians, engineers, computer specialists, 1,000 of them working together to do this over the last 25 years. This is not easy stuff. But the theoreticians that come up with this, and the best fit to this data, which is how they got 36 masses for one black hole, 29 masses for the other, is this one right here for Hanford and this one right here for Livingston. And you can tell they are pretty good matches because when you subtract one from the other, you get this little curve down at the bottom, which is basically the noise. True statement? So the theory is matching pretty good, and in fact, that and the fact that they got the same signal, the correct light travel time later in Hanford that they had gotten in Livingston, is what gives them confidence to say, this was not noise, this was not someone having a wreck out on the interstate nearby, this is real. Because the same thing, microscopic thing, hard to see thing, happened, and it fits general relativity theory modeling of that. So all of it put together, it took them from September of 2015 to February, just exactly 1 year ago today, to convince themselves that they could convince the scientific community that this was real. You never want to stub your toe in science, believe me. I think these guys are going to get a Nobel Prize one of these years, but because they were so careful. But this is how they did it. Now the curve you see down here at the bottom like I say, this is in the audible frequency range. This is from 10 to about 150 hertz. Middle C on a piano is 256 hertz. So this is pretty low frequency stuff here. But this is the plot of frequency versus time. The same time scale is up here. And you can see the frequency, just like we see it happening here, all does go up when you just measure the frequency for both of them, for both laboratories. Kind of interesting, huh? Would you like to hear what that sounds like? They have taken that voltage and run it through an amplifier and a speaker and given us audio of that wiggly signal. They've done it two ways. Like I say, it's low frequency. You can't hear 10 hertz where it starts, but you can hear 150, 200 where it ends. So they're going to play that for you, and it's going to be low, bassy stuff. And then they're going to multiply the frequency up into the middle of our hearing frequency range and play it again. And they're going to do it several times. Would you like to hear that? It's kind of fun. They call it a chirp at the end. There's the high frequency. There's the real thing. Chirp, chirp. Now, of course, the static in the background was the noise. You saw the noise also before the gravitational wave came in. That was the static that you were hearing, and then you heard whoop, the signal came in. It's nice when you can hear it, isn't it? Makes it real. Okay, here is the actual data. The top one is Hanford. Now there's no shifting or anything. This is the real data on the same time scale. You notice the times down at the bottom. It all happened in less than 0.2 of a second. The whole schmear. Here's the Livingston data, the real data. And then here are the two of them together after we have shifted the Hanford data. Now I can see it. Can you tell that sure enough the Hanford data came in a little later than the Livingston data? Can you tell that this is over to the right just a little further than this is by looking at it? Well, that's that 7 millisecond delay. Now don't forget, this is 50 milliseconds from here to here. It's only 7 milliseconds later here than it was here. So, but you can visually, we have very good acuity, and you can actually see, yeah, there is a little delay there. And so when they subtract that out, you get this beautiful overlay here. Now let's look at the left-hand scale. This is time, okay. This is what we call strain. And if you look, you've got about from peak to peak, let's take the bigger one, you're going from about 1 plus 1 to minus 1 strain. So that's a total swing. I call it a peak to peak strain of 2 times 10 to the minus 21. You see the little minus 21 there on the screen? It's a very small number. That's 2 with 21 zeros in front of it before the decimal place. A very small number. But we told you going in, and Einstein said, you'll never see that very small number. It's so small. But they did. So you can see, when they see it like this, they believe it. So how much did the mirrors move? Well, strain is defined to be the change in length of the light path divided by the total length, which was 4 kilometers, 4,000 meters. So we solve for the change in length. How much did it appear that they changed in length? And so we put the 2 times 10 to the minus 21, that's the strain, times the length, which is 4,000 meters. Do arithmetic. It's 1/10 the diameter of a proton, which is the center nucleus of a hydrogen atom. That's what they saw. Now, what did they see? I told you they had all kinds of control mechanisms to sense trucks, lightning strikes, seismic waves, you name it, anything that could be causing a vibration, they sensed it, and then they had actuators that control those mirrors to hold them stock still. They counteracted anything coming in. The mirrors never moved. They had sensors for everything. You won't believe what was in those buildings. And computers. What happened was the mirrors are stock still, all three of them. The gravity wave went through and made the space between the mirrors a little bit longer. Well, you know, 1% of a proton diameter longer, and then shorter, and then longer. A few times as it went through, and then it's all over. You saw it happen. You saw the signal. But that's what was going on. The mirrors were stock still. They have spent 25 years figuring out how to hold those mirrors stock still in special suspensions. The space between the mirrors changed because of Einstein's generalized theory of gravity. Are you beginning to see that first slide? Why this is beginning to be a little hard to imagine in our heads, but that's what happened, and that's the way you have to understand how this experiment worked. That's how small, and that's why the guy who invented it was kind of jumping up and down in his seat there at the end in that video. Okay, we first detected a gravitational wave September 14th of 2015 after lots of computations with the theory of comparing it to black holes merging, to neutron stars merging, to supernova, all these things that could happen, figuring out which one it was. It was two black holes merging. And then with a little more analysis, they figured it 36 and 29 solar masses for the two black holes. After that was all done, and it took them 4 months to do it, they announced just exactly a year ago today, we found it. They found another one the day after Christmas of 2015, and they announced it last June. Very similar to this, done the same way. I'm not going to go into that. And then, right after that in January, they shut down both instruments to start making further sensitivity and performance improvements to them so they can see even smaller black hole things and maybe some merging neutron stars. And it also has the effect of increasing the diameter of their universe. Don't forget this was 1.3 billion light years away. With more sensitivity, you could see the same thing even further away and still produce the same signal. And then they restarted it 6 weeks ago. So hopefully in another few months, after they do all their calculations and what have you, and confirm, we will start getting a steady stream of discoveries of more black holes. By the way, this one's called GW 150914, which means 2015, 9th month, 14th day. I already told you that, but that is the official name of this gravitational wave. So that's where we are. What are we going to do? Oh, let me show you here. I said it was in the large Magellanic Cloud. Here is their picture of the whole sky view. This is the Milky Way going through. And the one that we've been talking about, the one from September 14th, it came from somewhere in that zone of the sky. It turns out, I believe that right in here are the Magellanic Clouds. I think I can see the fuzz of the Magellanic Clouds. Do you see that, Mark? In the southern hemisphere. And then the one day after Christmas, they do not have anywhere near. Don't forget that 7 milliseconds that they measured from. That's, if you do your trig, if you know it's 10 light milliseconds direct as a crow flies from Livingston to Hanford, and this came in and took 7, and you do your trig, you realize it came in at 45 degrees. So somewhere on a cone, 45 degrees around that line is where it came from. They say it came in from the southern hemisphere, so they have picked that zone. But that's not good enough to tell the telescope operators around the world where to aim right away, because they have computers looking at these signals and quickly doing those calculations and alerting them within seconds. We think we got one. It's up to you to prove it, but we think we got one. It's got all the characteristics you told us to look for. That means they can get the word out very quickly, but they can't tell them where it is very well. So how do we do better? These two are right here in the United States. There's one in Germany. It's operational, but it's smaller and it's not sensitive enough to see this, to have seen these two. They're building one underground in a mine in Japan. They're building one that should come online in the next few years in Italy. And because of this success, the Indians that funded one, they're going to build one in India. Once we get this array of them all around the world, now we will be able to triangulate in on where these things really are. Two stations, you can't do it. But when you start adding up other observations, equally sensitive and precise, then you'll be able to home in. So there is an awful lot of astronomy yet to be done. And that's all this says. No practical applications that I can think of. It's too small. We can't even tell the acceleration of Neptune going around. But we're going to have a new world of astronomy. We may someday be able to see evidence of the Big Bang. We will certainly see pulsars and collapsing or merging neutron stars, these sorts of things, as they learn how to make these instruments more and more sensitive and what have you. And one of the ones that I showed you is actually 3 mirrors in space, 1,000,000 miles from Earth, where it should be very quiet, very little noise up there. The trick is going to be having them aim at each other and stay accurate and stay still and all this good thing. But this was a 4-kilometer arm to get this kind of precision. Think what they can do in space with satellites a zillion miles away from each other, being communicated with lasers. The future is here to unfold. Thank you very, very much for paying attention to all this. And we took another hour, didn't we? Sorry, it takes an hour. Any questions from anybody? No Einstein questions? Oh, I can't believe it. Well, it's been fun for me. I learned a lot. I hope your mind or your brain is not spinning around too fast as you try to imagine this stuff going on. But the reality of those signals and the way they did it, Einstein was right again. We proved it again. As I said in that last slide, one more proof that Einstein's general law theory is correct. Every time we try to measure it, we get his answer. So it's kind of amazing, like the guy said. Yeah.
How did they figure out how long ago it took place?
Good question. I think the main thing is that they've got, like I say, the theory is quite good now. The strength of the signal, you know, waves from a point, that's essentially a point source, 1.3 billion light years away, and it's a spherical wave that goes out. Of course, by the time it goes by Earth, as I said earlier, it looks like a plane wave because it's such a huge sphere. But the amount of energy that they detected and the amount that they figure was released, 3 solar masses, would have decreased to that amount in a 1.3 billion light year expansion of the wave. In other words, they can measure how much energy they got in their little detector, and that kind of tells them, and they know how big the source was from the theory of 2 black holes. They got the mass and what have you. The mass comes from the jiggle on the curve, so that's an independent thing. So knowing that, they can figure out how much energy was released, the 3 solar masses, and when you spread it out that way and you get this little fraction of it, you can figure, essentially using the 1 over r squared law for light, how far away it was. So I'm guessing that that's pretty close. I haven't read them say that exactly, but I'm guessing that that's how you would do it, is you just see how much energy did you get from this very energetic thing out there. And it's just like, you know, how we do the magnitude of stars. They fall off as 1 over r squared too. So if you want to know the power of a star in watts instead of its magnitude, you do it that way.
That's what I was thinking.
Corollary question. How did they determine the relative masses of the two? If there's an aggregate mass.
Yeah, and how did they know it was 3 solar masses that were radiated as solar energy?
Right.
And I really don't know that. That comes from the general relativistic theory of the theoreticians. You know, you saw their beautiful smooth curves that matched. Apparently that implies the rest of their theory is pretty good too. It's from that and the jiggles that they estimate the relative masses of the two, and there's something to do with the chirp, because when you read their papers, they talk about the chirp mass, and so apparently the rate at which it's inspiraling just before the coalescence tells them something about the masses that were inspiraling, because like I say, they come up with what they call the chirp mass. And there's a equation that I don't want to tell you about.
They had built a whole series of models.
Yes,
Of different
and the
phenomena.
computers are applying, you know, they're smoothing the curve, they're getting rid of the noises, but
Fit that model.
they are in high speed. They are trying various models on these signals. First to determine that they got the signals in coincidence from the 2 observatory. That's ground zero. And once they get that, then they start applying the models in high speed to try to figure out, well, okay, which kind was it? And then, of course, they have to, you saw it took them 4 months to refine all that. In this case, since it was the first one, they were double checking. They were checking all of the computer records of all the sensors that are around those 2 laboratories, sensing man-made signals or lightning or all that kind of, making sure those were all consistent and null, and that the mirrors were in fact just hanging there on their silicon threads, still, absolutely still, and that this was a space-time thing stretching that space between those mirrors. They spent a lot of time making sure everything was right before they said a word. And they can you imagine, they had 1,000 signs. They kept a veil of secrecy on this thing that was very, very good. The other scientists, you know, at MIT didn't even know if they weren't on the team. They didn't know. So they were able to keep the secret quite well for those 4 months.